Okay, then without further ado, I'd like to introduce Dimitris Koukoulopoulos from Montreal, who's going to talk to us about Galois groups of polynomials of large degree.
Thank you, Sean. Thanks a lot for having me to speak here. I'll speak about some joint work with Lior, Bary-Soroker, and Gady Kozma that has been ongoing for some time now, and it's in pretty final form now, and we should hopefully have a preprint in the next weeks. Okay, so here is the question. So we're given some polynomial f over the integers with some coefficients a, j. So I will be insisting that polynomials are monic, though this is not super important. And the aj's are random variables and independent from each other, and they all follow some given distribution, nu. Just pick your favorite distribution. But to keep things a bit simple, I'm going to assume that this distribution is the uniform distribution of some given set of integers n. And there are a few cases that this question has been studied quite a lot, and some famous cases are the ±1 coefficients, which are called sometimes little good polynomials. And there's a very nice recent work about their flatness on the circle. The 0-1 polynomials were studied in the 90s by Otlitsky and Poonen, and especially their zeros, when they have some very beautiful pictures about the fractal structure. And the third type of model one can consider is when one considers all integers up to between -h and h. And there are 2 points of view in this model. The one is to fix n and let n tend to infinity, which is sometimes referred to as the large box model. And the other point of view is to fix h and let n tend to infinity. And this is more the type of question I will be interested in, where the coefficients are restricted and the degree goes to infinity. And this is because the first question has been very well understood in the 20th century. So these are some questions I would like to consider. So one of the most basic questions one can ask is, well, what are the odds that f of x has some sort of non-trivial factorization? And a more sophisticated version of this question is, what can we say about the Galois group of f? So we'll be denoting with script g of f, the Galois group of f. And well, the general philosophy is that once you have a factorization, then the coefficients are have a lot of conditions, and so this shouldn't happen very often. So here is an example. Well, there is so one important thing is that it might have an obvious root, let's say at 0, because if we take the 0-1 coefficients, then the probability that the 0th coefficient vanishes is 1/2. So this should happen. This does happen with large probability, 1/2. But in this case, it should be the case that it is reducible exactly when the 0th coefficient vanishes, and other than that, it's not really, it doesn't have any factors. And in fact, even more strongly, it should be either that the Galois group is Sn with probability 1/2, or that it's Sn minus 1, because there is a trivial factor of degree 1. So modulo obvious roots, the Galois group ought to be as complicated as possible, with very high probability. That's the general philosophy. So here is what we know about the large box model when n is fixed and h tends to infinity. So the story here starts with van der Waerden in the 1930s, who understood that the probability that g of f is not the full Galois group is small. So he could save 1/6 of h on the power of h. And as a direct consequence, then you also get reducibility with very high probability. And this result was improved by Gallagher in the 70s using his large sieve, when he showed that the exponent 1/6 can be improved to 1/2. And turning to the similar question of whether f of x is reducible or not, Kuba showed that the probability is 1/h at most. And this is basically best possible because a root at 0 occurs with a probability about 1/h. And Gallagher's estimates were improved by Dittmann more recently, who showed that this exponent 1/2 can be made a bit bigger. So this is the result, 2 minus square root of 2. And he could also get even better results when the group has larger index. So he could have, okay, so this exponent should have a minus sign. So his result is approaching basically Kuba's result when the index goes to infinity. And I should mention that Rivin more recently showed that the Galois group is either AN or SN with very high probability, but he could, my understanding is of the status of the paper is that at this point it's not clear if the AN versus SN case can be distinguished. Something which, as you will see, occurs very often in this subject. Even though AN should occur with much lower probability than SN, it's very hard to distinguish between the two. And I would also like to mention a more recent result by Pham and Su that showed that for very general class of coefficients that the reducibility occurs with very high probability. In particular, they could, for example, take the set of coefficients to be the values of some polynomial. Okay, so these are pretty much what we know. These are the facts we know about the large box model, and our knowledge is pretty complete. So let me now move to the restricted coefficients case. So we'll be writing WHP to mean with high probability as the degree tends to infinity. And one of the earliest works on this was the Additive work, who conjectured in '93 that in the 0-1 case, you get irreducibility almost surely as soon as you condition on the zeroth coefficient being 1. And an important work on this subject was by Konyagin, who proved that as long as you condition to the zeroth coefficient not being 0, then with very high probability, you have only very large factors. So you could get n over log n. So I'm going to speak about Konyagin's work a bit more later because it comes into what I'm going to talk about. Okay, so the first case that we could actually show that someone could actually show that you get irreducibility almost surely in a restricted case was by Bary-Soroker and Kozma in a paper that was announced, I guess, around 2017-18, but only appeared this year. So they could get, they could do sets of the form, let's say all the integers up to 210. And why this particular one? Well, the significance of 210 is that it has 4 distinct prime factors. So they could actually get any length, any interval of length that has at least 4 distinct prime factors. And these 4 distinct prime factors is very important. It will come up again. And they could also prove that, let's say you have some h for which you could prove irreducibility almost surely. Well, then you could also prove that the Galois group is very big, and it's either equal to AN or SN with very high probability. So let's say they basically reduce this question to proving irreducibility, and then you also get the Galois group. And so the question was solved for arbitrary n, except for the case where n is a singleton, in which case we can't say anything, of course. But it was basically solved in its full generality by Brouillard and Varjou, who proved this, that as long as you condition on the zeroth coefficient being non-zero, and you sample them uniformly from any set of integers that are at least 2 of them, then with high probability you get irreducibility, and in fact you get that the Galois group is very big, either AN or SN. The dates here are messed up because sometimes the publication of this took a bit less time than the other one. But there is a catch, though, that they have to assume the Riemann hypothesis for certain Dennekit zeta functions. Okay, so the purpose of this talk then is to sort of go in the space in between. So I'm going to present some results where we can remove this very this condition that the length of the interval or a set has to have this very specific arithmetic structure, and we'll get much more general sets n, though we will not be able to get the full force of the result of Lior under Rh. The results will be unconditional. Okay. So here is the main new result. So conditioning always on the event that f of 0 is non-zero, then we get that the Galois group is either an or Sn with high probability in the following cases. So the first case is that we can do any interval of length at least 35. The second case is that we can do arbitrary sets that are sparse but not too sparse. So you can have at least, you must have at least 4/5 plus a little bit, h to the 4/5 plus a little bit, and h has to be big. But other than that, n can be completely arbitrary. So this completely removes any arithmetic structure from your set. And the last one is, so here one might wonder what is the best possible exponent that one can get. Can we push our method for sets of smaller exponent? And we can do this for an arbitrarily small exponent if we consider some special sets of coefficients, such as odd powers, and more general things, but this is the cleanest form one can state it. Okay, so the reason why S is odd is, I'm going to explain this later, why we cannot take squares. But I just wanted to say that we can also make our results quantitative, as in some of the previous results, and the probability we get is at least something polynomial in n. Do you have any questions so far before I start explaining some of the ideas?
What if the coefficients are not uniformly distributed on a set?
Yeah, so we can get sets. So the most general version of the result is that for aj you allow some probability measure mu j, and there is some condition on the second moment that basically boils down to this one once you assume it's uniform.
What if you take each, just building on the last question, what if you take each coefficient with a small probability? Does it help? So each, instead of 50-50 with probability p. Any sense that this is easier? Or?
You mean the 0, 1?
So yes, for example, the 0, 1. Yeah. So you get a sparser polynomial. Yeah. So the
more concentrated your distribution is the harder the problem. So you want to spread around the probability, then it's easier because you have more.
Okay.
I'll state the most general result later on, and then you'll see what exactly what kind of measures we can handle. Okay. So what is the main idea behind this proofs? So the proof will split into two parts, similarly to the Bary-Soroker Kozma earlier result. So the first part is to show irreducibility with high probability. And then there is a completely different argument to show that having irreducibility and small Galois group doesn't occur very frequently. So I'm going to first talk about the first part. Okay. So the very first thing one has to do is to get rid of divisors of very small degree. And for this, we already have Konyagin's argument. So we just need to adapt it to more general measures, which is not such a big deal. So it's really just Konyagin's idea generalized. So, so small degree means just you have some algebraic number here, omega, of small algebraic degree that is a root of your polynomial. So this is what you need to rule out. So you need to rule out, you need to understand this probability that f of omega is 0 for some omega. And then, of course, I can just write this as equation. And now I can interpret this as a sum of random variables, where the first random variable is a omega, a0, the second one is a1 omega, etc. So this is just some random walk. And we have very good estimates for concentration of sums of random variables. And the most classical one is the Kolmogorov-Rogozin inequality. Basically tells you the right-hand side is at most 1 over root n. And it turns out you don't want to use this for too many omegas. So we only use it for cyclotomic factors. So where omega is the root of unity of some degree, let's say up to n to 1 over 10. And for non-cyclotomic factors, we use, as Konyagin did, we use the Mahler measure and the fact that non-cyclotomic polynomials have Mahler measure that is just a bit bigger than 1. I don't want to get into the details because they're quite technical, but it's a really beautiful proof Konyagin gave. I strongly recommend it. Okay. This is all I have to say about small degrees. And now let me pass. So this argument basically allows me to assume that if there is a degree, a divisor, then it's of degree at least, let's say, n to the 1 over 10. So let's see how to treat this case now. So we assume now we have a factorization as g times h with, let's say, g is the smaller degree, the smaller polynomial of degree, let's say, k, or at least n to the 1 over 10. So the main thing to do is to reduce this modulo to some primes. This is where these different prime factors come into play. And then work in FP of x that where we understand much better the arithmetic, and we can count the reducible factors and all these things. And the key observation is that if you have, so let's say for simplicity, n is the set of integers from 1 up to h, and let's say p does divide h, then this new random variable, f sub p, is uniformly distributed among all monic polynomials of degree n with coefficients in fp. Okay, that's just immediate. So then I can use the results known for the arithmetic of polynomials over finite fields. And in particular, I can use the intuition that we have from the integers, because there is a very famous analogy between integers, polynomials, and permutations. And the corresponding result was, the corresponding question was answered by in integers already by Ford in around 2004, who proved that if you pick an integer m uniformly at random up to x, then the probability that it has a divisor of degree between y and 2y is about this much, log y to minus some constant delta, which I will write down later. And then there is some lower order degrees factors. Okay, so this is for integers. And then it turns out that the analogous question for permutations is the following one. So that the permutation fixes a set of size k. And why is that? Is because so primes, so integers factor in primes in the same way the permutations factor into cycles. And if you take products of cycles, then these are all the invariant sets of the sets that the permutation leaves invariant. So the size of these sets are somehow the sizes of the divisors of your permutation. And this analogy between integers permutation and how they factor basically allows you to translate this word into the permutation word and get the analogous result, where log is replaced by now the size of the permutation. And then there is a further analogy, which is with the polynomials over finite fields. And but here it's a bit more direct analogy, and basically it gives you the analogous result. So, and this was proven by Meissner, and here is this constant delta that occurs in all three results. It's about 0.086. Okay, so what do we learn from all of this? So I started with a polynomial f, and then I reduced it modulo p. And if the degree g of the degree of g here is k, then the degree of gp also is k, assuming everything is monic. So then the probability that f has a divisor of degree k in z is controlled by the probability that has a divisor of degree k in fp, and we just understood this. I just showed you how to understand this probability. So this is the lemma. The probability that f of p has a divisor of degree k is this much. And now this is not quite enough because I need to rule out any degree k that is bigger than, let's say, n to the 1 over 10. And I cannot just sum this overall k bigger than n to the 1 over 10. I'll just get something that is completely trivial, worse than 1. Okay, so here is the trick. You take r prime, let's assume that your length h is divisible by r prime factors. Then if I consider all the reductions of my polynomial f modulo these primes, then these are independent random variables that are all uniformly distributed over the corresponding finite fields, polynomial rings, over the corresponding finite fields, and they're independent of each other. And these all follow from the Chinese remainder theorem. Okay, so now here's the probability I want to control, that f has a divisor of degree k. And now I can just upper bound it by the probability that each of these fj's has a divisor of degree k. But then this union factors by independence. And I can use this lemma here to get this upper bound. So I multiplied 0.086 by r. And the key is to make, of course, this exponent bigger than 1. And it turns out that you need 12 primes to do that. So if you get 12 primes, then you get, as exponent here, something a little bit bigger than 1. And then you can sum over all n, and then you get, okay, I missed a 0 here. You get some savings. And so this is why 12, so this is basically the sketch of the proof. This is basically the proof of the Bary-Soroker Kozma result, assuming that H has at least 12 prime factors. So how do they go from 12 to 4? Well, they use an idea going back to Mantle, Perez, and Rivin about permutations that we can also translate in the polynomial setting directly. We don't need to go to permutations. So here is why 4 primes suffice. So with very high probability, when I take an f and I reduce it modulo p, this is a normal, a typical polynomial over fp, meaning that for each, and for us, this will mean that for each degree k between n to the 1 over 10 and n, then it has at most the expected number of irreducible factors of degree up to that point, k. And now, since it has at most this many irreducible prime factors, the number of divisors that are composed of them, so k smooth means that all the irreducible factors are of degree at most k, then the number of such divisors will be at most 2 to the log k, which is k to the log 2. Okay, and then this is smaller than k, so the probability that I hit a divisor of exactly degree k ought to be sort of small, and the naive guess would be just that you divide this through by k, because the divisors are sort of nicely distributed among all possibilities. And indeed, one can prove something like that, and this allows you to replace 0.086 by 0.3, basically, or 1 minus log 2, which is much bigger. And then 4 primes are okay. Okay, so what I get from this is that if I condition on the event that all of these reductions fpj are normal in the sense that they satisfy the first bullet point, then the probability that f has a divisor of degree k is at most the product of these 4 things, which is 1 over k to something bigger than 1. And then to bound the probability that f has a divisor of degree at least n to the 1 over 10, what I do is I first pass into this event, condition into this event that occurs with very high probability. Okay, so whatever is left is little log 1, and then use this upper bound on this conditional probability space. Okay, and then this is basically the proof in a nutshell. Okay. So how can one go So this works assuming that you have perfect distribution and independence here. So it works when h is 210, for example. But how can you make this type of argument work when h is, let's say, 211, which is bigger, so you have more polynomials, but then it doesn't have the special arithmetic structure? Okay, so here's what happens when you do h 211. Let's say what happens at the distribution of this modulo 5. So there is a little bit of bias. So the class A is 1 mod 5 occurs a little bit more frequently than the other classes. But really, it's not that much more frequently. It's very close to 0.2 all the way. And this is, if I interpret this, the left-hand side as a periodic function modulo 5, and I consider its Fourier transform, the point is that it has a very small Fourier transform at every non-zero frequency mod 5, just because it's essentially the uniform distribution. And then, so what am I doing? I'm picking polynomials from whose jth coefficient is modulo 5, something very, very close to being uniform, but not quite uniform. And thinking of this, so thinking of these coefficients as sort of the digits of my polynomial, one can imagine that the ideas from the literature of polynomials for polynomials with missing digits can be adapted to this setting. So for polynomials with missing digits, so for integers with missing digits, this was done by D'Arthez and Mauduit, and then more recently simplified and improved by Maynard, their work. And already Moses and Porritt had independently carried this argument over to the polynomial setting. And we can use this circle of ideas to handle situations like that, where you have some primes where it's not quite uniform, but if you look at the Fourier transform, it's uniform enough to so that this kind of machinery can push the argument through. And what you actually need is a level of distribution, meaning that you need to control. Okay, so you need to exclude, for irreducibility, what you need is to exclude divisors up to degree n over 2, just by looking at the symmetric one. So you basically need to understand how, if you reduce the modulo 4 primes, you need to understand what are the chances that your f has a divisor modulo 2, let's say G2, a divisor G2, and modulo 3 has a divisor G3, etc. for 5 and 7. And if your polynomial, if these reductions F2, F3, F5, and 7 were completely uniformly distributed and were also independent, then this probability here would be given exactly by this ratio, by this quotient. But it turns out you don't need it to be exactly that. You only need that on average when you take the difference and put absolute values and you sum over all possible degrees of divisors here, of degrees that go just a bit past 1/2 times n, then you want to get some sort of savings, and something like that will suffice. Okay, so how does this more general case work? You use this, so first you use this machinery developed by D'Arthez, Mauduit, Maynard, and Moses and Porritt, and actually a lot of other people, to get this type of an estimate. And once you have such an estimate, you can use sieve methods and what we know about anatomy of integers and polynomials to just make the argument I sketched before go through with only approximate equidistribution modulo 4 primes. This is basically the proof in a nutshell. And so if you happen to be an expert on digits with primes, you will know that you don't really need such a strong condition. The coefficient, the Fourier transform to be really small at all non-zero frequencies modulo 5. You need something weaker, an L1 bound that is weaker than this. So I'm going to now show you the main theorem that is between somehow the master theorem that every other theorem follows from. Okay, so this is the theorem. so we assume that for our set n, there are 4 distinct primes. Let's call them P1 up to P4. And let's call the product capital P. And what is it that we need? We need that once we take the Fourier transform, not just modulo P, but we also need it for all divisors Q, non-trivial divisors Q of P. Okay, and there is some shift here with whatever is left. This is more technical, but you can just think of L as 0. So basically, this is the Fourier transform modulo Q of our set, the L1 norm of the Fourier transform. And what we need is that this summation satisfies this strict inequality, cardinality of n times square root of Q. So what is the trivial bound here? Well, I have Q possibilities for K, and the completely trivial bound on this summation is the cardinality of n. So what I need to do is to win a square root of Q over this completely trivial bound. So once this happens, then basically one gets the result I stated before, that you have joint approximate equidistribution modulo 4 primes. And so the methods can go through and get irreducibility almost surely. And as a matter of fact, you can also get Galois, AN or SN almost surely. And so the fact that this inequality is strict is actually very important. We do need it to be strict. We need a little bit more than square root cancellation. So a set like the squares is off limits, at least now, because it's really a set, the squares are always exactly square root at the square root level. So you cannot get this kind of estimates working. And so this is why we cannot get the squares, and this is why we can get odd powers. And this is because if S is odd and it's co-prime to P minus, and then I pick a prime such that P minus 1 is co-prime to S, and I look at how n to the S behaves modulo P, then this behaves basically, it covers all of FP. So it behaves essentially like a linear polynomial. So I can pretend that my S is 1. So it's a cheap trick. You get from, it's because you can treat it as if it were an entire interval. Well, this condition is very flexible, and you can check it for many sequences. You can take a polynomial sequence, polynomial set n here, and check if it satisfies this condition or not. And actually, I've checked numerically, and it looks like polynomials of degree up to 3, of degree exactly 3 with coefficients between 1 and 10 satisfy this for some primes. You can find primes. Okay. Yes, and finally, how do we handle the general sparse sets n, where you don't have a specific formula for your set n, you just know that it's not too sparse? Well, then you use the fact that you use the large sieve to deduce that for most primes, for most 4 tuples of primes, your set n is not, is actually well distributed modulo them, and you get, so you can get this inequality for almost all tuples, P1 up to P4. Okay. Right, so are there any questions? Because now I'm gonna pass to the Galois group. So this is how you get the reducibility, and this is the most general theorem we can get. And now, how do you go from irreducibility to controlling the Galois group? So I already told you before that Bary-Soroker and Kozma had a result that did this when the set n is 1 up to h, and now we need to do this again as in the previous, as in this theorem, we need to do it for more general measures. So how do we handle more general measures? Okay, yeah. So this is what we've proven. We've proven that f of x is irreducible, and we want to assuming that f of x is reducible, we want to prove that the Galois group is big. So of course, the reducibility is equivalent to transitivity of the Galois group. So what we want to show is that we want to use this transitivity to show that the Galois group is big. So here is the key result that we need. So Juchak and Piper proved that this quotient Tn over Sn is little of 1. So what is Tn? Tn is the union of all the permutations contained in some transitive group, subgroup of Sn, that is not An nor Sn itself. Okay. So it turns out that if you even if you take the union of all of these groups and you calculate the probability that a permutation lies in them, then this is a low probability event. So given this result, this is our new goal. So what we want to show is that because f of x is random, then we want to extract from it an element gf in the Galois group that behaves sort of uniformly in Sn. Because if we can do this, then this is our new variable gf that behaves uniformly in Sn. And we know that with very high probability cannot lie in Tn from the result of Juchak and Piper. So this is the strategy. So how do you extract from an irreducible polynomial this permutation that has good distribution properties? To do this, one uses a bit of Galois theory and specifically ideas around the Chebotarev theorem. So let us fix, to begin with, let us fix a prime P for which the reduction of f modulo P behaves well, is well distributed in Fp of x. So this prime P will be forever fixed. So we have fixed it and we know that now we have a nicely distributed polynomial, though the distribution might not be perfect. And then attached to this polynomial, we can attach two things. The first one is that we can attach the Frobenius automorphism at P. And the second thing we can attach to is this partition. So we can factor Fp modulo P. And we just gather all the degrees of the irreducible factors and make a partition out of them. And it's a partition because the sum of these dj's is equal to n. And standard Galois theory tells you that, first of all, if f of p is square free, which occurs with positive probability, then this partition pi f is just the cycle type of gf. Okay. And because PF is sort of, because FP is sort of uniform, PF behaves sort of uniformly among all behaves as if this PF will force GF to behave as if it were uniformly distributed among conjugacy classes of Sn. So generically, this is not quite what happens. You do not just have that pi f is the cycle type of GF, but you have that the cycle type of GF is close to pi f, where this is a technical thing that you basically have to merge. So you have these degrees, and you have to put together some degrees, maybe. So if I have degree 1, maybe the cycle type of GF doesn't have 1, 1, but has 2, because I put 1 and 1 together. So instead of 2 cycles of length 1, I get 1 cycle of length 2. So this occurs if you have, this type of things occur if you have multiplicity of roots. But this is a technical thing, so just you can basically ignore it and think of, oh, so I have this explicit partition of n with the degrees of my polynomial fp, and then I have this Galois element gf that is pretty close to being pi f. So what I need to show is, the goal is then to show, we want to use the fact that this, the permutations contained in Tn to show that with very high probability, GF is not in Tn. And one of the main difficulties in doing this, so to adapt this, there are two main steps one has to carry through to carry out. The first one is that, first of all, we don't have uniform distribution anymore, so we cannot just use the Yitzhak-Piber result. And second, we don't just have that, we don't want to exclude only that G of F is not in Tn, but also any partition, any permutation whose cycle type is close enough to GF. So it's a stronger statement. It's because of this uncertainty here, because of degrees that can be big, of big multiplicity. But the good news is that because degrees of big multiplicity occur with very low probability, you can basically assume that GF is really close to pi f. So there are not too many other permutations to consider.
This wrinkle with this thing is generically true. Is this to do with repeated factors mod p or something?
Yes. So this is the main strategy. Okay, so how do we now do this? So here is our goal now. So we have a random partition, pi is a random partition of n, meaning just a vector of things that sum up to n. And the probability distribution of this is some nice measure nu. Where nice for us means that it's not too different from as if this random partition corresponds to the cycle type of a uniformly chosen permutation of n. This is what nice means. Well, there's a much more technical version of this nice that I'm not going to get into. So what I want to show is that for such nice measures nu, the probability that there is a permutation G in some transitive group other than an or Sn, and whose cycle type is also simultaneously close to this permutation pi. So this event occurs with low probability for all these kind of nice measures. This is the strategy. And so basically this is what we show. So so there's a more general version of this proposition, but for the purpose of the application to the theorem we want to prove is that this relation star holds if this measure nu is the induced measure by pi f, where pi f is the factorization type of f modulo p, and where p was chosen so that fp is close to being well distributed over fp. Okay, so you fix some prime p such that you know that f of p is well distributed among different congruence classes, and the divisors occur with the right proportion. And for such fp, you consider the new random variable pi f, which is just the factorization type of this. When you gather, what happens when you gather all the degrees? Okay, so this new random variable pi f is a partition, so it induces a measure nu on the space of all partitions of n. So and basically for this special measure nu, it's nice enough so that this star thing holds. As if it would also hold if the measure nu, this fp was uniformly distributed over fp of x. So the case of uniform distribution over fp of x is the work of Bary-Soroker and Kozma. Now we need to generalize this to the case where the distribution is close enough to being uniform. And this is the strategy. Right. And there is a much more general result that I'm not going to state. There are very few axioms one can write down that your measure nu needs to satisfy to obtain this generalized Yitzhak-Piber type result. That is useful when you deal with Frobenius elements. Okay, so we want to show Right, so pi is a random partition, and we want to show that, to disprove, or to show that the probability that G, so that there is some cycle type close to P that lies in some transitive group, that this event occurs with low probability. So the proof splits into two cases according to whether the transitive group is primitive or imprimitive, as it's very common in this type of, in this literature around the Yitzhak-Piber result. And the nicer and easier, more conceptual case from the point of view of anatomy and permutations is the imprimitive transitive, the case of the imprimitive transitive subgroups. Because what are these groups? These are subgroups of G that preserve a block structure. And what does this mean? It means that there is a decomposition of the integers from 1 up to n into some blocks, R blocks, B1, B2, etc., up to BR, that they all have equal size n over R. And these blocks are permuted by G. This means that B1 as a whole is either sent to itself B1 or to some other BI. And the same thing for B2. It's sent to some BI prime. So these are very special groups that have, whose permutations have this very nice structure. Okay. And we want to show that the probability that it doesn't, so we want to show that the probability that G lies in such a group is very low, even if we're allowed to modify G a little bit. So the prototypical case is when R is 2, and the first prototypical case is when R is 2 and G fixes both these blocks. So it sends B1 to B1 and B2 to B2. In this case, I have found two invariant sets of my permutation G, B1 and B2. And recall that invariant sets are analogous to these divisors. And there is this result of, for example, the result I mentioned earlier of Eberhard, Ford, and Green about how frequently they can occur. So here we need to show a generalized version of this where we're also allowed to modify a little bit G. But this is not such a big deal. And you can prove that this prototypical case too occurs with low probability because the probability that the random permutation fixes something of length n over 2 occurs with low probability. And yeah, so this is in symbols what I just said in words. Okay, so this consists a negligible set of partitions pi that they fix some set pi and some set u. Okay. And the second prototypical case is when this G permutes B1 and B2. And what happens in this case is that to have a cycle, all cycles must have even length, because if I start from B1, in order to come back to B1, I must do this at least an even number of times, because like one time I always go to B2, so I have to come back, etc. So all the cycles are divisible by 2. And it turns out that this is a low probability event as well. And because basically cycles are Poisson Poisson distributed, kind of sort of independent, and this also occurs with low probability. So in both these prototypical cases, you can conclude that they concern a very small set of partitions pi, and you can just remove those. And any other case, okay, is treated in sort of similar ways. And I'm not gonna get into the other details. And what about the primitive transitive groups? So in this case, we use the fact that these are very, so if a permutation G lies in a primitive transitive subgroup other than AN or SN, it must move around a lot of elements. So the degree of G is the number of elements that G moves around. And if you are in a primitive transitive subgroup of AN, of SN that is not AN nor SN, then there must be a very high, it must contain at least one element of high degree. sorry, all elements are of high degree. I messed this up. The minimum degree is big, not a, yeah. Yeah, so the minimum degree is big. So for all G, this holds, not there exists one. Okay. So for a normal permutation partition pi, this means with very high probability, we can use some sort of anatomical arguments, probabilistic arguments, and show that they must have some prime that is sort of big. Let's say this quantity I put here is not so important, and basically this prime p divides one and only one part of this of your permutation pi, of your partition pi, only one part. Let's call this part k, and we can also guarantee that this part is not too big. Okay, so this is a probabilistic argument. It's not so bad. You prove it, and once you have this result, then what you can do is now let's look at the G, at the permutations G that occur that are relevant here. What happens for these permutations G is that I'm only merging, to obtain the cycle type of G, I'm only merging parts of pi that are of equal size, but then there is only one part of length k. So there is, the consequence is that G also will only have exactly one cycle of length k that is divisible by p. And then you can basically cook up from this element, you can cook up a new element of your group G that is a cycle of length precisely k. And because we chose k to be smaller than n to the 1 over 3, we get a contradiction to this lemma here. So this is the argument for primitive transit subgroups. You show that they must move around too many things, but then they can't really. So this is the idea. Okay, so this completes the proof, and let me just summarize what I've discussed. So the first part of the argument was to prove irreducibility. And how did we do this? We started with a random polynomial f, and we eliminated the probability that it has a factor of small degree using the Kolmogorov-Rogozin concentration inequality and Dobrovolsky's results on the mother measure. This was Konyagin's idea. The second step is to reduce f modulo 4 primes, for which the set of coefficients n has small reduction, small Fourier transform. So basically show that, okay, so that this condition that it has small Fourier transform, just ignore this. The condition that n has small Fourier transform implies that f modulo p is roughly well distributed among monic polynomials of degree n over fp, and this gives ideas the domain are Moses emporic. And then the final step is to feed this into sieve methods and to use sieve methods and ideas about anatomy of random polynomials to finalize the proof that irreducibility occurs with very high probability. So this is a simplified version of what Bary-Soroker and Kozma did in their earlier work, and it also uses ideas of the work of Mandler, Perez, and Reilly. And the Galois group part, assuming we know that it is irreducible with very high probability, then we fix some prime p modulo which n has small Fourier transform. Well, from the previous slide, we have 4 of them, so just pick one of them. And the consequence is that fp is well distributed over fp. Then once it is well distributed over fp, you construct a partition pi f that is just constructed by factoring fp modulo over fp. And then you use Galois theory to construct the Frobenius element gf and show that the cycle type is close enough to pi f. You only need to merge a bunch of equal parts of pi f. And then use probabilistic arguments to show that pi f must satisfy some nice anatomical properties with high probability. And assuming that it is nice probabilistically, it is normal, you can use some group theory to eliminate that it lies in some transitive subgroup. That any permutation whose cycle type is close enough to pi f can lie in a transitive subgroup other than AN or SN itself. So this is pretty much the proof in a nutshell. And that's all I have to say. So thank you.
Thank you, Dimitris. Let's all try unmuting ourselves and clapping. Does anybody have any questions? Maybe I'll start with a technical question. So when you quoted Konyagin's results, you gave this n to the 1/10 thing. I thought Konyagin's result was good up to like n over log n, something much higher.
Yes, but you do, yes, but it's a much more complicated version of what I said. This is the simple Konyagin argument.
Okay, so it's just a simplified proof as it is.
Yeah, so if you care about this, what the optimal C n to the minus C savings this argument can give you, you might have to go through the hardcore version of Konyagin's argument. But there is so this much simpler version has the benefit that it's very easy to keep track of uniformity things. And so we have a uniform result where so we can allow the support of the measure, let's say it's between -8 and 8, to grow quite fast in terms of n. And to do that, you need to use this other version of Konyagin's argument. And this other version, it allows you to go up to h to be up to exponential of n to the 1/3 or something like that.
I see. So is it in that same paper of Konyagin, the simpler argument?
Yes, it starts with that.
So I had a question regarding your master theorem. You had a strict inequality, where it's essentially the size of n times the square root of q.
Yes.
And you said that that is critical to have the strict inequality there.
Yes.
So even a factor of 2 would ruin the argument. Is that right?
Here, a factor of 1.0001 would ruin the argument. Yes. Yes, correct. So you really need a little bit more than square root cancellation in order to get a level of distribution more than 1/2.
Right, and this has this is related to the fact that you have it's a discrete Fourier analysis that you're performing here.
Yes. Yeah, exactly.
I have a very naive question about this bound, actually, which is just intuitively it seems like the square root is on the wrong thing. The thing in the absolute value seems to be the thing that you should get, like square root cancellation. Can you say anything about that?
Okay, so if I give you, right, so for any set, so you just need to find some primes for which you have square root cancellation. So for most things should have something like square root cancellation. And there should also be a distribution. So you should be able to get a little bit more and a little bit above and a little bit below that. But proving this for very sparse sequences seems to be very hard. So here is a simple version of this problem is take n to be a set of polynomials, the set of values of a polynomial. And then basically this reduces, because of periodicity, this simplifies, and you can basically assume that n is mod q and then replace the n by f of n. So you have the values of the polynomial weighted by 1 over q. You need to win something of that. And so if you do something like the Veil conjecture,
I see. Okay.
You'll get square root of q, but then and it seems that only the it looks like only the very special polynomials that have squares in them only are in the way, but I don't know how to prove that.
Did you have any thoughts about the AN versus SN problem?
No, I've not seriously thought about this problem. Trying to finish this work, but yeah, it's a hard problem. That's you have to disprove that. You have to show that something being a square is occurs with low probability, which seems it ought to have any. You should be able to do that, but you're stumbling over such a sparse set of coefficients that it's not so easy.
Does anybody else have a question? If not, then let's thank Dimitris again for a beautiful talk.